Not exactly. In fact, my own experience with you is very different. You are very punctual in time, and you are very much, keen towards learning new things also.
Sir, that is part of our job also, and the way that our branch is getting evolved, and it is like multidisciplinary.
Of course, of course. And specifically for the people like us, means who graduated 2 decades before, the challenge is more, getting updated every now and then.
Uh, but I recall you were the very first person, some 7-8 months before, when we actually approached you for this Untitled FTP. You very readily consented that I'll take a session, and it was since then we are empowered and charged.
Thank you, sir. Thank you.
So Hardik sir is our coordinator and convener. So Hardik sir, can we start? Shall we?
Yes, sir. Good afternoon, Dr. Hirain Patel, sir, and
Good afternoon,
sir. Priyanka, ma'am.
Yes, sir. We are 46 participants. Shall we start, sir?
Yes, ma'am. We should start.
Okay. A very good afternoon to one and all present here. It is my privilege to introduce and welcome you all. I would like to introduce Dr. Hirain Patel, sir. He is currently working as principal at Vidush Somani Institute of Technology and Research since July 2019. Before this, he worked as a professor and head of the Computer Engineering Department of LDRP Institute of Technology and Research, LDRP ITR Gandhinagar, for 2.5 years. Before that, he worked for SP College of Engineering as professor and head of Computer IT Department for more than 11 years. He was also a Dean Faculty of Computer Science at Sakarchand Patel University and Chairman and Board of Studies for Computer Engineering and Information Technology departments. He was Chairman BOS for Computer Engineering at North Gujarat University, Patan. He has obtained his doctorate degree, PhD, in Computer Engineering from National Institute of Technology, that is SVNIT Surat, with expert area as cloud computing. For post-graduation, ME with the specialization in microprocessor, sir completed from MS University, Baroda, and graduation BE Computer Engineering, sir completed from Sardar Patel University, BVM, Vallabh Sir, having more than 22 years of teaching experience and have 75 plus research papers in various conferences and journals of national and international repute. One of Sir's paper has been awarded Elsevier's Best Paper Award. Sir is supervising PhD candidates, delivering numerous expert talks at various organizations. Sir also acted as a reviewer and session chair for many conferences. Sir's area of interest are cloud computing, parallel programming, computer networking, research methodology, information security, technical communication, IoT, and blockchain. Now, I would like to request Dr. Hirain Patel, sir, to share his expertise with all participants. Over to you, sir.
thank you, ma'am. How do I share my screen? Do you need to unshare first, or can I overwrite it? You have your screen already shared.
No problem, sir. You just click on the share icon, and your screen will get shared over my screen. Okay. I already unshared.
How about now? Is it shared now? Is my screen visible?
Yes, sir. Your screen is visible, sir.
Okay, great. So good afternoon to every participant. Thank you, Chirag Thakur sir, Adik Mulia sir, Priyanka ma'am, and all the faculty members back there at GC Rajkot. In fact, if I straight away move on to my topic, that is blockchain technology, specifically mining and consensus protocol, I'll be talking on. So if before I started, basically there are two parts in my presentation. First part is mining part, and second part is the consensus part. So before I move on to those mining and consensus, technically, I would like to acknowledge two courses from where I've got motivations for this lecture. The first course is from NPTEL, that is Blockchain Architecture, Design and Use Cases by Professor Sandeep Chakrabarty from IIT Kharagpur and Professor Dr. Praveen Jayachandra from IBM Research. In fact, now this course is not there in NPTEL. They have, I don't know, but they have a different course in NPTEL. This course is not available, but I guess the new course is also having some, Professor Sandeep Chakrabarty as a resource person. So this is the first NPTEL course which I would like to acknowledge over here. And second is one Udemy course which I loved a lot, blockchain A to Z, learn how to build your first blockchain application. So that's from Hadlin and Grill. So these are the two courses I would like to acknowledge over here before I move on to my contents. Let me make a disclaimer also, because many third-party copyrighted materials are being used over here, but the usage is fair use and that is for educational purpose only. So I appreciate your understanding regarding this. Yeah, out of many different publications in area of blockchain only, I would like to mention two over here. If time permits, I'll go to those publications because some of my lecture contents are from these two publications. So both are there on Science Direct. So first one is a blockchain state of art, architecture, use cases, consensus, and challenges. The link is also mentioned over here. And second one is we are working on a specific domain, that is agriculture domain. So we are trying to provide different solutions using blockchain technology specifically for agriculture domain. So second paper is Agri on Block, wherein the full title is Secure Data Harvesting for Agriculture Sector using blockchain technology. So these two papers are already available online on Science Direct. Apart from this, there are many other papers which are in conference and journals on blockchain, but these are the two main papers I would like to highlight. And if you are interested in looking into more papers, you can always go on my blog hbpatel.in, wherein you'll find all my details, including my email IDs and contact numbers and everything. So just hbpatel.in is my blog for that, and all those different papers along with video lectures and other stuff is available over there. Okay, and some links which I'll be using over here, I have mentioned just for the sake of your reference only. So these are the links I'll be using during the lecture just to make the concept more understandable. So I'll get back to these links later on once the topic starts. Okay, so let's get started. Mining and consensus. So I hope things are well. If anything is like, if I'm not audible or if the screen is not visible or if the audio is lagging, just please let me know by interrupting the lecture so that I can cope up with those issues.
Sure, sir. Sure, sir.
Thank you, ma'am. So basically, as I said, my talk is of two broad directions. So one is mining and the other is consensus. And I was looking at the full schedule of this STTP, and I could see that there are around 3 or 4 lectures already done on this blockchain technology. So I hope the fundamental part has already been covered. So I won't be going into those basic things of blockchain, and I'll be skipping them. But however, the things which are important from mining and consensus point of view, that I'll take little time to explore them. So there may be little repetition of some content, specifically hash functions or kind of stuff, but it won't take more than 5-10 minutes. So that's the first disclaimer. So mining and consensus, as you know that blockchain is a very simple concept wherein we are having blocks which are put together to form a chain. So this is a very simple concept. So this is a simple chain, and the chain is having 3 blocks. And now you already know a lot of stuff, like these blocks are having data or transactions in it. The blocks are having some block numbers and all those stuff. So I'm not repeating those stuff. So basically this one is a block number 1 or block number 2. So you can go like this. All right. And now the thing is, I want to add one more block. OK, next block. So what's the procedure? So currently I'm talking with respect to Bitcoin, but this can be applicable to any other blockchain also. Why am I saying Bitcoin? Because the proof of work algorithm that we will be talking later, that is applicable to Bitcoin. So that's why I'm saying Bitcoin. Otherwise, this is a general concept. It can be applicable to any blockchain. So there are 3 already mined block, already added block into the chain. Now the thing is, I wish to add a 4th block. So the thing is, who is going to add and how it is going to be added. So there are many different people. When I use the word person or people, you should use them interchangeably. This could be a person or group of person or even organization. But combinedly, I can call them as miners. So these are our, we'll be talking more about mining little later, because this is just an introductory slide. So I want to keep it as simple as possible. So you can consider them for the sake of simple understanding. There are 6-7 different people, 6-7 different person. It could be 60, it could be 600, it could be 6,000. So this could be, as I said, it could be an individual person or a group of person or an organization whose work is to mine the block. So right now, mining, you can consider mining as creating a block. So these 6 different person are, trying to create a block number 4. They all wish to add, they all want their block to be added over here as number 4. So supposing out of these A, B, C, D, these are all the miners. Right. So out of all these miners, supposing 3 miners could create a block. Let's say A, C, and D could create a block in time, because we'll see later on that you do not have infinite time to create a block. You are given very specific time. Specifically, in case of Bitcoin, you have hardly 10 minutes to create a block. So within that time limit, if you are creating a valid block, then you have a chance of getting your block added into the chain. So let's say this A, C, and D, these 3 blocks are created, and these 3 blocks are valid, legitimate, they are okay. Now so this process, the process of creating block is called mining. This process of creating a block is called mining. So this is the first part, the mining part. Now out of these 3 legitimate block, which block will be added over here, whether it will be A or it will be C or it will be D, because we cannot add all those 3 blocks together because they might be having repetitive transactions into them. So either I can add A, C, or D. So how do I decide? So for that, there comes the concept of consensus. All right, consensus is nothing but, in our simple English language, it is an agreement that if there are 3-4 different friends wanted to go for, maybe out of 5 different friends, 2 are saying that let's go for tea and 3 are saying let's go for coffee, then if we follow the principle of a majority, then 3 would win over 2 and all of them, the 5 friends, will go for coffee, something like that. So it's a very simple understanding, very primitive understanding of consensus, means agreeing on a specific decision, agreeing on a specific value. So consensus is all about deciding out of these 3 different legitimate block, which block will be added. So this is a primary idea behind these 2 words, mining and consensus. So if I quickly repeat in 1 or 2 lines, mining is all about creating a block, and consensus is all about deciding which block. If at all we are having multiple blocks, it may happen that I am having only 1 block which is legitimate. In that case, I don't have any other option, so I'll be adding that block. But if I am having multiple blocks which are legitimate, which are valid, in that case, selecting one of those blocks would be a part of this mechanism, which is called consensus. So this is the basic idea about mining and consensus. We'll explore more in little detail about the mining also and about the consensus also. Okay, so like if we quickly start, as I said, I won't be repeating those introductory parts. So I hope that you already know what is blockchain and all those stuff. But broadly, if someone has to learn blockchain, right, what I understand is first he or she would understand the cryptography. Specifically, of course, there is, I attended the last lecture from Padmaja ma'am also. So she did talk about hash and some symmetric key encryption and all those stuff. So cryptography is something from where you start learning the stuff, and hash is very important. And we know that in cryptography, basically those who are having some network security background. So we know that confidentiality, integrity, and authentication, these are the three broad aspects of cryptography. So confidentiality is something which is not used over here in this blockchain. Why? Because in blockchain we want everyone to know everything, and confidentiality is all about hiding. Okay, so confidentiality is about hiding something. It's about non-disclosing something. But blockchain is transparent stuff. Means we don't want anything to be hidden. We want everything to be known to everyone. So confidentiality is something which we'll not be using over here. All right. Yeah, and integrity. This is something which is very important over here. So integrity is about, you must have heard the word immutability. So immutability is something wherein once the transaction is done, once the process is committed, then there is no way you can roll it back. So roll it back or erasing the transaction is not possible in blockchain. So if by mistake, if A has sent B, let's say some BTC, let's say one BTC, okay, and later on A felt that, okay, this was the wrong transaction, so it cannot be rolled back. There is only one way to roll it back, means you'll have to make another transaction wherein the same BTC, the one BTC is been transferred back to A. So integrity, or the word immutability, comes over here. Once it is written, once the transaction is done, so once the process is committed, there is no way you can go back. So that is about integrity. And to achieve integrity, the algorithm or the concept is hash. Okay, and the algorithm is SHA-256. So this is something what we'll be talking more about. Under hash also there are many different algorithms like MD4, MD5, but message digest algorithms are a little weaker and it has already been broken. But so far as SHA-256 is concerned, SHA-256, secure hash algorithm is the full form of SHA-256. So it is till date it has not been broken, and it is considered as a very strong hash algorithm, and it is being used in Bitcoin also. Of course, we have SHA-512, SHA-128, but SHA-256 is very much in use, and we'll be talking about SHA-256 only. And the last part is authentication, wherein the digital signature and all those stuff would come, the symmetric and asymmetric encryption and all those stuff would come under authentication. So this is just the basic stuff about hash. So someone would start from hash cryptography, and then we would be moving to immutable ledger, because this is the basic idea about the blockchain. So the second part, so I hope you guys are okay with all this stuff. So I'm not going into the detail of immutable ledger. And then the ledger would be deployed on distributed peer-to-peer network. So the next part would be distributed peer-to-peer network, because the idea, the nature of blockchain is distributed and decentralized, because there is no one who is controlling the entire blockchain. Right? So that's the third part. And so after these three different parts, and as I said, I hope you are okay with all this stuff. The next part would be mining. And the last part would be, consensus mechanism. So this is the last two part I'm going to cover in the today's lecture, but I would like to give you the overall idea or the chronology or the sequence in which one should proceed in the domain of blockchain. All right. So let's go. As I said, you already know what is the basic stuff, so I'm not repeating all those stuff, but the things which are essential for this talk, I'm just quickly taking them. So I hope this is very much easy for you. Like block. So block is comprising of various components. So out of all those components, we'll be taking the components which are very important to us. Like the very first one is the block number. So it would be a unique and mostly auto incrementing a number. So that is uniquely identifying a specific block. So it starts from 1, 2, 3, 4, 5, 6 likewise. All right. And then I'm having all those transactions over here. So you consider that as a data or you consider that as transactions. So a block is having group of transactions. All right, so a lot of transactions are put over here. Like in case of the marketry concept also, we are having all those transactions over here. So transaction 1, transaction 2, transaction 3. All right, so all these transactions are, because transactions are something which are happening every now and then. If back in some corner of that if Mr. X is sending something to Mr. Y, all right, like some Bitcoin, something like this. All right, so this is one transaction, and there are hundreds and thousands of transactions going on every second. So these are all transactions which are queued over here, and all these transactions are to be put into the block. Right, so all those transactions tx 1, 2, 3, 4, so all these transactions are put over here. All right, and then at the end, because this is a block, so we are having one previous block also. So the hash of previous block we will be putting over here. So this is my previous hash, and this is nothing but the link to the previous hash. So I hope you know that part. All right. So of course, along with a lot of other information, these are the main information which is required for creating a block. And when I put all this stuff together, and when I create a hash function, all right, when I use the hash function, I'm going to get some hash for this one. So this is what I call it current block hash. All right, so this can be considered as a message. All right, and this message is the entire part, this whole part. If I consider that as a message, okay, so I can use hash. As I said, hash could be SHA-256. So SHA-256. So I could use this to create a hash, and this is nothing but my current hash. All right. So this is the simple idea of a block. Right, and this is a very simple idea. It means it looks like, if it is so simple, why there is so much buzz? All right, so the buzz starts from here. Like if I try to change something over here, let me try to change. Let me ask myself, can I change the block number? No, I cannot change. I cannot change the block number. All right, because it is something which is given by the system. All right. Can I change the transaction? Of course not, because otherwise what will happen? The fundamental idea of immutability would violate. Okay, so I cannot change this one also. Can I change this previous hash? No, you cannot change, because previous hash comes from the previous block. All right, so I cannot change this. So in short, this current hash is fixed in nature, because it depends on something which cannot be changed. It depends on block number, it depends on data, it depends on previous hash. So, and I cannot change anything. Right. So the thing is, current hash is pretty much predicted in this case. Pretty much predicted. Why? Because this thing is already fixed. Previous hash is already fixed. Block number can be predicted. If the last block was 1000, all right, next block number would be 1001. All right, and these transactions are also public. The transactions are also public, means everyone knows the transaction. All the miners know the transaction. All right, so it is very much easy to predict. It is very much easy to compute hash, current hash. So what to be done to make it more secure? So there is an introduction of extra, what do you call it, a field, right? So of course, along with all the other fields that we have just seen, right? We have just seen the block number. So it is already there. We have just seen a previous hash. So it is already there. Okay. Data is also there. So data and transaction, whatever you call it interchangeably, no problem. So data and transactions are there. But now I'm adding an extra field over here, which is called nonce. So nonce is basically, those who are from computer security background, computer networking background. So they know that it's a number used once. Mostly it's a random number, though random is not word used over here, but it's a random number used once. So it would not be repeating again and again. Right. So now there is a nonce. So now if I repeat my concept of computing, current hash. So now you know that now block number is something which cannot be changed, data which something which cannot be changed, previous hash cannot be changed. So what can be changed is nonce. Nonce is in your hand. Nonce is something which is given to you. Now you decide the nonce. All right. And based on the nonce, now once you decide the nonce, you can create current hash. So obvious question is, how can I decide nonce? Means what if someone thinks that the nonce should be 5. Okay, someone is taking nonce is 5. Someone is taking nonce equal to, let's say, 500. Okay, what is wrong in both of these? Nothing wrong. Both the nonce are right. If you use nonce equal to 5, then also you are going to get some hash value. If you use nonce equal to 500, then also you are going to get some other hash value. Okay, then how do I decide whether 5 is appropriate, 500 is appropriate, or something else is appropriate? Okay, so this is a question, all right, of this is a basic foundation background about the mining part, because now the thing is we have message over here. Message is comprising of 3 parts. The block number is there. Block number is there, then data or transaction is there, data or transaction is there, and previous hash. The 3 part combinedly make a message. Okay, these 3 parts combinedly make a message. Message along with now the nonce. Message along with nonce, I'll be putting it in a hash function. As I said, hash, we are talking of SHA-256. Okay, so hash function, and that would give me h. That would give me hash value. So this is the basic idea. So now one may argue that, sir, things are still simpler. Okay, this part is already given. This part one may guess, or one may predict, or one may use any random number like 500 or 5000, whatever. This part is already there, so we are going to get some hash value. What's wrong with that? Nothing wrong. But to compute the hash value, we have certain conditions. Okay, we want my hash in certain form. We want my hash in certain condition. Right, we'll see in a little while what answer do I want and how would that affect the decision of non-selection. All right, so this is the simple idea of introducing an extra field nonce in the block itself, and nonce is a kind of variable. By changing the value of nonce, I would be controlling the final hash value, and the final hash value is something which is very important for me. So this is the basic idea without nonce and with nonce. Now, if I move forward, so let's talk about the hash function itself. All right, as I said, you must have, like, hashing has already been covered, and the SHA-256 is something what we will be talking. So I hope that this has already been covered. So if I quickly take 2 or 3 minutes to summarize the hash function, we'll be putting our message over here, right? Message into this SHA-256 or any hash function. Okay, and what am I going to get is the hash value. Okay, so this is your message and this is the hash value. Now this could be variable in nature, like it could be few bytes to it could be few kilobytes, or it could be few megabytes. It can go in any size, not an issue. But the hash value would be fixed 256 bits in case of this SHA-256. In case of 512 also it would be 512, but let's talk of SHA-256. So irrespective of the size of input, the output would be 256. So this is something which you already know. But the beauty of this hash function is not this one. The beauty of hash function is something different. Over here, if I represent this so hash function, message, and it gives me hash value. The simple three things. Okay. Now there are certain characteristics. I'm sure you know these characteristics, but because it is necessary, I'll take 1 minute to explain them. So first characteristic is the hash is of fixed value. Okay, so that's very simple thing. Hash is of fixed value because in our case it is 256. Okay, so this is done. That means it's a simple characteristic. Second characteristic is computationally, this function has to be computationally efficient. Computationally efficient means fast and speedy. It means in simple language, it has to be a fast or it has to be a speedy. Wherein, irrespective of, 5 byte of data or 500 KB of data, it should give me the hash 256 bit in no time, in ideally no time. All right. So that is computationally efficient. Second is the beautiful characteristics are these 3 and 4. That is pre-image resistance. The pre-image resistance. This one is the third one, which makes the hash function, very much utility function for this. So given H, it is hard to find. If message is given, you can always find out hash. But if hash is given, you cannot find out message. This is what they call it pre-image resistance. Means if given H, you cannot compute message. Okay, of course, using message you can always compute hash, but this is what you call it irreversible property. Irreversible property of hash function means you can go this way. From message you can always calculate hash, but from hash you cannot calculate message. This is pre-image one, and second one is second pre-image resistance, wherein given a message M1. Okay, given a message M1, is given. Okay, and if I use hash over here, I'll find out H1. So I am having now H1 with me. So can I find out message M2 such that the H of M2 is again the same H1? So no, you cannot find. This is practically infeasible. Theoretically, you can use all those possible combinations, but practically it is not possible. So you cannot have same M2 for which the hash of both would be same. So it is not possible. So these two properties makes hash a beautiful function to be used in this blockchain technology. And of course, collision free. One more property is there, collision free. Collision free means if I'm having 1000 messages, M1 to M1000, or it could be 1 million. So for M1, I'm getting hash code H1, and for M1000, I'm getting H1000. But in all of this, you will not find a single hash code repeating over here. Single hash code. So means if it is being repeated, it is called collision. For two different messages, we are getting the same hash function. So if it is so, then we are saying it is a colliding. So two different messages colliding on the same hash value, but this will not happen. All right. And the last one is avalanche effect. So avalanche effect is something wherein a small change in input would result into a huge change in the output. So I hope that you already know this stuff, the hash function, but I wanted it to be repeated because this is going to be used in my case. All right, so now let's come to the mining part. So far as this mining is concerned, all right, because we have started from the hash function. So hash function would be, in our case, SHA-256. SHA-256 would be giving output of 256 bits. All right, 256 bits is a long number. So for the sake of understanding, if we take only 4 bits, for time being, we consider it a 4 bit so that we understand the concept. Later on, 4 bit can be extended up to 256 bit. So for 4 bit, what are the different combinations that we know? That 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 1. Let me just write it down. This is important to understand the mining part. 1 0 1 0 1 0 1 1 1 1 0 0 1 1 0 1, then 1 1 1 0 and 1 1 1 1. All right, so we know that this is a 0 to all the way up to 15. Okay, so 0 to 15, and in case of hexadecimal, we start from 0, and then this one is 0 1 2 3 4 5 6 7 8 9. Then instead of 10 we use A, B, C, D, and this one is E, and 15 is F. All right, so we also know what is hexadecimal part. This one is binary part. All right, so thing is, for 4-bit output, for 4-bit hash function, we can have 16 different options. So in case of 256, we can have 2 raised to 256 different options. So it's a huge number, so it cannot be accommodated over here. All right, so the thing is, now what do? There is a concept of pull of hash. Now this is something what you should be concentrating upon. Pull of hash. Pull of hash means we are having all those possible hash. Supposing my hash size, like the bits, supposing bits are in our case 4 in this example, then I am having total 16 different options. If I'm having 5 bits, then I'll be having 32 options, and likewise. And later on, I'll go up to 2 raised to 256 option. This is my final version, but I cannot show that 2 raised to 256. So I'm taking the example of 4-bit. Now what do? We put all those possible hash, because these are all the possible hash values. If we are having 4-bit thing, these are all the possible values. You cannot have anything outside 0000, and you cannot have anything beyond 1111. So what am I going to do is I'm going to put all those numbers over here, something like this. 00000010, then 0010, then I can go like this also, I can go like this also, it's up to you, no problem. So 0011, 0100, this is a pull of hash. I'm just putting all those hashes one by one over here. 0110, 0111, 1000, then 1001, 1010, 1011, 1100, 1101, 1110, and 1111. So these are the first 16, hash over here. Fine. Now, if I quickly draw a simple line over here, okay. Let's say if I draw a line over here, then can I say that everything below this line is having minimum 2 leading 0? Everything below this line is having minimum. I can have, but this is for sure. Below this line is I'm having minimum 2 leading 0. You can see this 2 leading 0. We are having, of course, more, but at least 2 leading 0, at least 2 leading 0, something like this. Okay, like if I use second, so in this case, let's say this is 2 leading 0. Now, if I use another one, suppose if I draw one line over here, this is simple understanding. So can I say anything below this is having at least one leading 0? One leading 0. So yes, you can see that all those numbers, all those possible hash value below this one, 1, 1, 1, 1, 1, 1. Yes, we are having 1. All right. So this is just for the sake of understanding that we can organize all those possible hash values and we can create a pool of hash wherein this part is having the minimum hash. That means all those 0. If I'm having 256 bits, then all those 256 bits over here 0, 0, 0, and this part is having the maximum one. Means all those 256 1 will be over here. All right. So this is how you pull off hash. So this from this place, let us try to move on. Now, what will happen? Let me redraw that part, and rather than now 4 bits, let us try to understand in general. So now let us assume that it is 256, and now the total possible hash values will be 2 raised to 256. So it's a huge number, and let's hope that all those, like all 256 zeros, starting from this to all those 256 1, starting from all the way ending over here. So this one is maximum and this one is minimum. But you can visualize from my previous example that all these possible hash values, every hash value having total size equal to 256 bits are put over here. Okay. Now the thing is, now we draw a line over here. Now this line, what I call a target line. Later on, I'll use a word difficulty line. Right? Now I use a word difficulty line. Now, why is it so? Because anything below this would be having some common property. Some common property in what sense? As I said, leading 0 property. Leading 0 property. Okay. Supposing if I take this one, then all these hash value may be having leading, because if I take 2 different lines, let's say this one also. Okay. So this line also. So maybe, over here with the red, I'm having leading, if it is 256 bits, so leading 80, for example, let's say leading 80. This is just an example. Okay. But if I go up over here, there may be leading 40. There may be leading 40. In our previous example, if you remember, okay, the down we move, we are having more number of leading 0. The up we go, we are having less number of leading 0. Okay. So what's the use of all these leading zeros and all this stuff? All right. So the thing is, now let us try to understand from the perspective of a hash. So what is given is just a second. Now you are having a message M along with the nonce Nonce. I think if you remember, and we are going to apply hash function and we are going to get some H hash value, and hash value would be somewhere over here. Hash value would be somewhere over here. Okay, because these are all possible. This is a complete pool containing all possible hash values. So it would lie somewhere over here, somewhere over here, somewhere over here, somewhere over here. No problem. I can have a hash value from this pool. Okay, so if you quickly move over here, look at this. All this, the message, the block number, data, transaction, previous hash is fixed. What is in your hand is the nonce. Okay, so this is fixed, is given. You do not have chance to change it. So there's nothing you can specifically do about it. But so far as nonce is concerned, it is in your hand. Okay, so it's a variable. You can select, you can choose. All right. So let's say I'm selecting 10. I'm selecting 10. And for this, if I select nonce equal to 10, okay, and this message, then I'm going to get H. So H could be over here. Let's say this is the 256-bit hash where the nonce equal to 10. Okay. Now, if I change nonce 10 to 20, okay, I may get this output. I may get this output where nonce equal to 20. Then for nonce equal to 100, I may be getting this hash value. For nonce equal to 1000, I'll be getting this value. For nonce equal to 5000, I'll be getting this, because this is completely unpredictable. There is no pattern at all. All right, so this is a basic idea that depending on the value of nonce, you are going to get different value of hash. Okay, so it is up to you what nonce you are deciding, what nonce you are selecting. We are going to get some hash value. So the question is then, is there any specific relevance of selecting a specific nonce? Like if Mr. X is saying that, okay, I'm good with nonce equal to 10, and Mr. Y is saying I'm good with nonce equal to 20, then what's wrong with both of them? No, both of them are fine. But the thing is over here is now there is a concept of puzzle. Okay, of course you use this simple equation, but now the final output that you are going to get, the hash, it has to have that h, this h has to have minimum some d leading 0, d leading 0. Okay, so d could be, let's say, for the sake of understanding, 4. Okay, so let's say 4 leading 0. Okay, so if this is the condition, if this is the condition that you cannot have any hash value, so just try nonce equal to 10, then I'm going to get this value. Does it have 4 leading 0? No, so I'm not going to discard. Let me assume one more, because you cannot, as the nature of hash function is very unpredictable and very random, so you cannot just simply keep on incrementing that. For let us take n equal to 10 now, then take n equal to 11, 12, 13, 14. You cannot go like that. You will have only one option. You can randomly select the value of nonce and just keep on guessing. This is complete guessing work. This is complete, a work of, luck only. There is no mathematics applied over here. Okay, because it is the beauty of hash function SHA-256 that there is no way you can predict the value of hash based on your original message or even original nonce. So the only option with you is just keep on guessing all those different values of nonce. 10, you take 10 now, then let's take 1000 now, then 5000 now, then let's take 6. Just keep on guessing. And the moment you get hash, all right, which is, satisfying this condition, that yes, now for you are getting some hash wherein you are getting initial 4 leading 0 and then A, B, C, 1, 5, 6, 7, something like this. If this is your hash, okay, that you are going to get, then this is something what you should be looking for. All right, so for something, this could be over here, this could be over here, something. So it is below your target line. It is below your target line. All right, so this is the fundamental idea of mining, specifically using hash. Okay, so now there are two main questions. Now, the first question is, how do I decide target or difficulty? All right. So the other question, like how do I decide nonce, has no relevance. So I hope you would not ask that question, but you are going to just keep on guessing the value of nonce. So that question is not valid at all. But the question is, how do I decide target or how do I decide the difficulty? Like one may say that let us take leading 4-0. Okay, one may say let's take leading 8-0. 8-0, then one may go up to leading 20-0, something like this. Okay, so how do I decide this? There can be maximum 256-0 because the total size of hash is 256. All right. So you can go, theoretically, you can go up to 256 over here, but practically we would not be going all the way up to 256 because otherwise it would be almost impossible to, crack that mining puzzle. Okay. So the thing is, first, let us try to understand if I keep leading 40, 80, and 20, what will happen? The complexity would increase. The complexity would increase because the more leading 0 matlab means you are having less option. We are having less option. If you have carefully observed that mining pool, okay, if you are carefully observe the mining pool, so if I take target this, then this may be having 8 leading 0. If I go up, this may be having 5 leading 0. If I go up, this may be having, because now I am having more values over here. So this may be having 3 leading 0, something like this. So 3 leading 0 is over here, 5 matlab 3 is already there, in 8 3 is already there, something like this. So if I increase the leading 0, the options that I am having, the possible options that I am having, or the possibility of finding a specific hash value from that particular chunk becomes complex, becomes difficult. So in short, more leading 0 means more complex problem, less leading 0 means less complex problem. So then what to keep, how to decide this difficulty? So for that, let me take you to one slide which is very important for you, this one. All right. So in this slide, I'm not sure whether you have seen it or not. If you have not seen, then also this is a very simple slide. Back in 2009, this guy, Satoshi Nakamoto, like we do not know whether he was a guy or girl or maybe an organization, but let's, for the sake of that, Satoshi Nakamoto back in 2009, defined everything. Okay, and it has got a complete mathematics till 2014. So in 2009, he decided that for every block, it should take only 10 minutes. All right. 10 is not exact 10 minutes. It could be 8, 9 minutes, 10 minutes, 11, 12. But normally every block should be created within the range of 10 minutes. So in 2009 also this was there, and 2040 also this was there. Means with increase facilities in terms of computation power, the thing is you cannot have multiple blocks within 10 minutes tenure. Okay, no matter what you are using supercomputer, you can only create one block in 10 minutes, right? So that is something for the sake of restricting everything, for the sake of restricting. Now, so for 10 minutes, so in 1 hour you can have 6 blocks, and because 1 hour is 60 minutes, so 10, 10, 10, 10, 10, so it's 6 block. And per day, because when you multiply this 6 with 24, okay, what you are going to get is 144 blocks. Okay, and then when you multiply 144 with 365, what you are going to get is almost 52,560 blocks per unit. Right, so this is for first year in 2009, and initially, if you create one block, we are going to get 50 Bitcoin as a reward. So the internal revenue generation would be 50 Bitcoin multiplied by this 52,000 something. So it would come down to this many Bitcoin. All right. So these are the currency generated internally. All right. Okay. Now next year the same stuff, but next year the earlier 52,000 was already there, and now this new 52,000 is added. So now it would be this much. So this plus this equal to this one, and then again the reward would be same. But when we add the last reward and this reward, these two things together, I'm going to get this one. All right. So it was in 2009, 10, 11, and 12. Now for these 4 years, he has decided everything for 4. For 4 years, what you are marking is now I am reducing the reward by half. Okay, so earlier for creating one block, we used to get 50 Bitcoin during 2009, 10, 11, and 12. But now during 2013, 14, 15, 16, you are only going to get 25 BTC. Now, same way for 2017, 18, 19, 20, what you are going to get is 12.50 BTC. And in 2021 to right now, we are in 22. So current reward per block is 6.25 BTC. All right. And likewise, it went on, calculating. So later on, we are going to get 0.39 BTC in 2040. So now the thing is, how do I, because practically this table looks very simple, but obvious thing is in 2009, the computational facility was different. In 2022, we are having much higher computer compared to 2009. So obviously that's something which we used to create in 2009 in 10 minutes. Obviously in 2022 in 10 minutes we can create much more block, but still Nakamoto restricted that part, restricted that no matter what kind of equipment you use, no matter you are in 2022 or 25, 30 or even 40, you will only be creating one block in 10 minutes. So this restriction is possible because of the concept of this difficulty. Means if you are having more capability, okay, we would increase the complexity of the problem. So even if you are having higher computation power, you will not be create more than one block in 10 minutes. So whether even if you are in 2040 and you are having much higher computer, no problem, we would be increasing difficulty for you. All right. So this difficulty is a kind of variable that is adjusted. That is adjusted based on the number of blocks created in 10 minutes. All right. Supposing let us take an example. Okay. So if in last 10 minutes, if in last 10 minutes, this 10 minutes, okay, we created two blocks. Let's say we created two blocks. Okay, that means the problem is simple. The puzzle is simple. Thus, Nakamoto expected the user, the miner, to create only one block. So in this case, what will happen? The difficulty will be increased. Difficulty will be increased. But if in last 20 minutes, I could create only one block, that means Nakamoto expected the block to be created in 10 minutes, but it took 20 minutes. So the difficulty is too high. In that case, the difficulty is reduced. So it's not always that the difficulty is increased. It can be increased also, it can be reduced also. All right, the restriction is this one. We want to make sure that the block created should be within the tenure of around 10 minutes, if not exactly 10 minutes, 7 or 9, 10, 11, 12. So that's fine. But if it is taking 1 minute to create a block, that means the puzzle is very simple. All right, in that case, make it complex. If it is taking too long, like 20 minutes, 25 minutes, 30 minutes, then in that case we will assume that the puzzle is very complicated, people are not able to solve it. So let's make it simple so that they can solve it in 10 minutes. So this is how this particular equation, in fact, this is, if we can look at from economical perspective also. So this has been very wisely drafted so that even inflation part is also taken care of in this. Otherwise, what will happen? The more computational power, you would be generating more blocks, you will be getting more rewards, and there won't be control on those cumulative reward. So this, like RBI printing those currencies. So RBI cannot just print currency in a haphazard way. They have very specific calculations. Same way in this one also, Nakamoto did everything very deliberately so that the the things are under our control. Right. So yeah. So I have one slide wherein I have written what I just explained. The difficulty is adjusted every 2016 block. Okay, every 2016 block, matlab for one block you need 10 minutes. Consider for one block we need 10 minutes. All right. So for 2016 block, all right, it would be exact 2 weeks. So every 2 weeks, they will review the difficulty. Every 2 weeks, every 14 days, they would review the difficulty. How they would review? As I said, if they are taking less than 10 minutes, we would be increasing the difficulty because puzzles seem to be simple. And if they are taking too long, if the puzzle is difficult, then we will be decreased. So the question is very simple. If the previous 2016 blocks took more than 2 weeks, if it took more than 2 weeks means the puzzle was very difficult. They took more time. In that case, difficulty is reduced. We'll make it simple. And if they took less than 2 weeks, matlab the puzzle was simple. They did it way before the time given. So we will be making it more complex by increasing the difficulty. So this is how the difficulty is either increased or difficulty is either reduced based on the the review of last 2 weeks outcome. Did the 2016 block took more than 2 weeks or less than 2 weeks? All right. So now I have a couple of links over here, which I guess would make the things a little more clear. I'm not sure whether I can directly move on to that part or not. Okay, is my other screen visible or same PPT is visible?
Sir, this is the same PPT which is visible.
Okay, let me stop this presentation. Let me just go ahead and is my browser visible now?
Yes, sir, your browser is visible.
Okay. So this link is already means I have shared it earlier. So this bitcoinity.org. So this is nothing but the difficulty graph, Bitcoin mining difficulty. So you can see all the way from 2017, and we can check from 2009 also, not an issue. So we can go all the way from 2009. But the initial days where means nothing was actually happening in Bitcoin. So let's talk from 2017. So you can see in and all the difficulty is increased. It means if you take it in general, the difficulty is increased, but it is not increased all the time. See, somewhere over here, it has been gone down over here. And then because it took more than, at this place, it took more than 2 weeks. So like the system thought that the puzzle is very complex, so they reduce the difficulty so that they can be completing everything within 2 weeks. All right, and then again slowly, because the thing is, this is the slow increment in the difficulty is due to the enhancement in computational technologies. Like if you are working with Core i3 or Core i5, Core i7, obviously you are going to get better computation power. Okay, and if you have better computation power, you would be doing the same task in relatively less time. So in general, it is increasing, but sometimes if it is too hard, then there is an option of reducing also. Okay, so this is the difficulty chart. All right, now if in the same block size, then look at block size is not very important over here. Time between blocks, let me check this. Okay, so time between block. Okay, so we know that every block should be created in the span of 10 minutes, but as I said, it is not exactly 10 minutes. Sometimes if you look at this particular block was created in 8.30 minutes, 8 minutes and 30 seconds, whereas this block was created in 11 minutes and 90 seconds, something like. But somewhere if you average it down, it would be around 10 minutes only. Okay, and this plus and minus are due to the two different facts. Obviously first is the difficulty, and second is sometimes the guessing works as I said, the guessing part, the mining part is not 100% mathematics. It is on luck also. You select some random nonce, and your day is good, and you get the desired that hash value immediately. In that case, it would take less time also. All right, and sometimes it would take more time also. So this chart tells you that every 10 minutes we will be creating a block. All right, and can you see my PPT back now?
Yes, sir. PPT is visible.
Okay. So now this blockchain.com's, let's explore it. Okay, so if I go on this site, okay. All right. So if I this is our latest thing, right? Like at 2:33, this particular hash has been computed, right? So I can click on any stuff to look at it. Okay. And all other things are simple. I should not be going. I would like to restrict myself to the mining part only. Okay, so yes, there is a hash over here. I'm not sure whether this part is visible to you. Can you see this hash?
Yes, sir. It is visible.
Okay, so now because this is in hexadecimal, hexadecimal means there are 4 bits. We have already seen that if it is F, it is 1111. Okay, so now look at this. How many zeros are there? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So there are total 19 leading hex. But when you convert into bits, 19 multiplied by 4. Okay, so it is almost 76 leading zeros. Okay, so this is our current difficulty, 76 leading zero. So currently, if you really want to become a miner, if you really want to create a block, in that case you would need to find out a hash value which is having 76 leading zero out of total 256. The total size of the hash is 256, but out of them you need to have 76 leading zero. All right, so if your hash is having 76 leading zero, then you are done. Then your block is mined and you are going to get 6.5 BTC as a reward for that particular block. All right, so this is something which I wish to tell you so far as mining is concerned. So at this point in time, so before we go to consensus part, which is my second talk. Should I take 1 or 2 questions from the audience so that at least one part is over?
Sure, sir. All the participants, please, you can raise your queries if you are having any. Sir is going to entertain the answers.
There is one question already written in the chat box, sir. Can we opt for the hash size of 128, 256, 512, 1024, etc. before mining? In fact, that depends on the hash function that you are using. As I said, in case of Bitcoin, the system uses SHA-256 hash function. So you do not have any other option rather than keeping the hash size 256. All right, if you are creating your own stuff, all right, or some other cryptocurrency is using SHA 512, in that case we may go up to 512. So it is strictly dependent on the hash function that we are using. Any other question, they may just type in the chat box so that because consensus is little different than the mining. So I just would want to make sure that before I move to consensus part, at least mining part is completely understood.
Clear. Yes. So I request all the participants, in case you are having any query, you may type it into the chat box, or you may unmute your mic and speak. So we are having one question in the chat box. What happens when two or more miners solve the puzzle at the same time?
Yeah, this is a really wonderful question. In fact, how could I forget that? Okay. In fact, yeah, the answer of this would come in the consensus part because, yeah, this is very much happening stuff. And because of this only, we are having consensus mechanism. Because if I'm having only one miner and only one solution, then there is no problem at all. Okay, but because this is a distributed network means one person is sitting in the Australia, other person is sitting in China, third person is sitting in Canada. So there may be a little time lag before the actual block is communicated, before the actual block is propagated across the network, and it may happen within that fraction of second or 1 or 2 second. There may be multiple actual legitimate blocks which have been created. So I think I did tell you initially, if I am not, yes, in this case, for example, A, C, and D, they did create 3 legitimate block almost at the same time. So in the answer to that would come in consensus mechanism. All right. So we would be talking about that part in consensus mechanism. So that is perfectly a valid question. We will be looking at the questions answer in next 5 to 10 minutes. Any other question?
Sir, we
Okay.
are having
Who
one more
decides on
question
the
in chat.
difficulty level? How it is being decided in the distributed network when there is no authority? This is also a very good question. In fact, because we are talking with respect to Bitcoin, and this Bitcoin is completely a non-central, like no one is controlling at all. So this particular difficulty is an equation, is an mathematical equation wherein the difficulty is auto adjusted. It is an equation, as I have just explained in my last presentation, like last slide. Like if we look at the last 2 weeks thing, like the 2016 blocks should be completed in 2 weeks. Now there can be, they could have taken less time and they could have taken more time. So if they did less time, means the puzzle was simple. But in next question is how much less time? For example, rather than 14 days, 2 weeks is 14 days. So rather than 14 days, did they complete in 13 days? Did they complete in 12 days? Did they complete in 11 days? If it is 11 days, then it was very simple. In that case, increase that difficulty little harder. If it is 12, increase, but not up to that 11 part. So there is an equation which auto adjusts. It's like the manual switch that we used to have in our older radio. We used to adjust the frequency in radio. So this equation is like that switch. It keeps on adjusting the difficulty every 2 weeks based on the output of last 2016 blocks creation time. Right. Any other question? So I hope there is no more questions. So let's move on to the next part. That is consensus. Okay. So consensus, as I said, it's an agreement. Basically, it's an agreement. Like if there are 4, I said in the very first or second slide, if there are 5 friends, all right, and they wish to go out for like tea or coffee, but they do not have common consent. Okay, so like these 3 people are saying that let's go for tea, and this one is saying, these 2 are saying that let's go for coffee. So in that case, either they can toss a coin, something like this, or they can take a majority opinion, like in this case majority is tea, so they would all go for tea, something like that. So this is a simple idea. The idea of consensus is very simple. All right, but at the same time, proving it mathematically would be much difficult, right? So definition is very simple: the procedure to reach to a common agreement. Okay, in a multi-agent system, obviously, because when there are multiple agents or multiple entities or multiple participants, and specifically in distributed or decentralized, because if it is a centralized mechanism, then we can give this responsibility to the server. Okay, everybody submits their request to server, and server would be having authority to decide whether to do this or that. But in this case, we do not have a centralized mechanism. It's purely distributed, wherein peer-to-peer communication is there. All right. So in this complex environment, how to achieve a distributed consensus? So this is the main problem. So this is just a definition what exactly we are targeting. All right, now to this understand distributed consensus. I guess you must have heard this Byzantine fault tolerance mechanism in one of the previous lecture. I guess the last expert, Ms. Joshi, also said about Byzantine fault tolerance. So this is something from where the concept of distributed consensus comes into picture. Right. So Byzantine, that word comes from the emperor, like, we have Roman Empire, then we had those who are interested in history, they might be knowing Byzantine Empire, and then Ottoman Empire, something like that. So that this word basically comes from that empire, Byzantine Empire. Okay, so the Byzantine fault tolerance mechanism is very simple. I hope someone must have shown this part, but because, as I said, which is something which is relevant to me, I would taking few minutes to explain that. So I would take 5 to 10 minutes to explain Byzantine fault tolerance, because unless otherwise, it's difficult to understand. So the concept is that the problem is very simple over here. The problem is there is a kingdom over here, or castle, something like this. The castle over here, the kingdom over here. Okay, and the enemy or the other means there are 4 different generals over here. The war generals, what we call them. Okay, there are 4 different generals from the same army. These are from the same army. They have surrounded this castle and they want to have victory over this castle. All right. So let's give them name: General 1, General 2. They are having different troops. Okay. So General 4, General 1 is having 1,000 soldiers. General 2 is having 1,000 soldiers. Something like that. They are having different troops. All right. But they win. This particular army win only if they attack at the same time. If G1 attack, okay, and G2, G3, G4, if they do not attack, then in that case, this army would get defeated by this kingdom. All right. So there is a condition that if they attack all of them, at least 75% or 75% of them attack at the same time, they would win. Otherwise, they would get defeated. All right. So out of these 4 generals, this one is master general or commander, you can consider. And there can be a traitor also. Traitor, matlab in our case, it's a faulty node. Faulty node or malicious node. Faulty node is a different. Malicious. Let's consider malicious node. Malicious means it would behave unnaturally. So this one, you can consider this as a traitor. All right. So now this master, the master can also be a traitor. We will be looking at that option also. So master can also be a traitor. So now General 1 or master or commander, he feels that we should attack on this kingdom. So it issues order of attacking to the other 3 generals that let us attack. This this is called message passing system. Means they may even directly call on the phone, or they send via message, something like this, because there is no specific one-to-one communication link between them. All right. So let us assume that they have somebody who takes their message and pass it on to that G2, G3, G4. Okay. Now, because G2 is a traitor, all right. So what G2 would do, it would not give the same to other, like attacking. Attack is the command from the general, but G2 would say no, let us not attack, let us retreat, means back off. So G2 is saying that let us not attack, let us back off or retreat. Okay. But G4 and G3 are genuine ones, so they would be just communicating what they have received. So attack has been received by G3. So G3 would say attack on this one. G3 would say attack to this one. Okay, same way. Sorry, this one is G4. Same way for G3 also. G3 would say attack to this one. G3 would say attack to G4. So this is a complete diagram over here. Now let us try to understand whether the attack would actually happen or not. Okay, so general one, yeah, it's a master one. So anyway, he is going to attack because he has issued the order. So general one is going to attack. Yes. Okay, general 2 is a traitor, so he's not going to attack anyway because he knows that we are supposed to attack, but because it's a traitor, he would not attack. What about general 3? So general 3 has received, one attack, okay, from G1 attack, then G4 attack, but from G2 it has received, from G2 it is received retreat. So even if we follow the majority principle, then it is a 2 attack and 1 retreat. So it is going to attack. G3 is going to attack. And same for G4. G4 is also going to attack because G4 has received attack from G1 and attack from G3, but retreat from G2. So G1, G4 and G3 would be attacking and G2 would be silent. G2 would be silent. So the concept is if majority of them are attacking, then they are going to win. So the ultimate output of this war would be winning. Okay, they are going to win. So this is the simple idea of Byzantine fault tolerance mechanism. When there are multiple entities and they wish to reach to a common consent. Consent could be over here. There could be two options so far as this example is concerned. Okay, consent is either attack or consent could be or retreat. Even this general one can issue the order of retreat also. Not a problem. Okay, so they can. But the thing is, if the order given is attack, the majority entity should follow attack, and if the order given is retreat, then majority of the entity should retreat. If it is the case, then they are going to win, or at least they are going to be safe. In attack case, they are going to win, or in retreat case, they are going to be safe at least. Okay, so this is the case. Now, what if the master is, as I said, traitor? So in that case, what will happen? If master wants to attack, it would tell everyone to retreat. And in that case, what will happen? Retreat would happen. But if retreat is, agreed, then in that case also they are safe because nobody is attacking. They are just sitting idle. So say, and if it wants to retreat, but master is, giving the order of attack, and if all of them G2, G3 and G4 except the master, because master is anyway traitor, and so it's not, even if it has issued attack, the G1, the master is not going to attack, but the other three G2, G3 and G4 are going to attack, and because with the majority of principle they are going to win because out of 4, 3 have attacked. All right, so this is the idea of Byzantine fault tolerance in distributed consensus, because G1, G2, G3, these are 4 computers you can assume, and they have message passing mechanisms among them. They do not have direct connections and all those, no central authority. All right, and there could be a malicious node, and no one knows who is malicious. Right. So what if there are 2 traitors? Now in this example, when there is n equal to 4, n is number of computers or number of generals. Okay, so up to 1 traitor, that is fine, because if 1 traitor, then there are 3 regular nodes. Okay, regular nodes. This one is malicious node, so this is fine, no problem. But what if there are 2 traitors? Then the system is not going to work, because now it's a 50-50 stuff, 2 traitor and 2 regular. Okay, so even if you do this kind of exercise, is because majority are not going to attack. In case of this, 50% would attack, 50% would not attack. All right, and even this regular would get confused what to do, because 50% they have received, to attack and to retreat, so they would not be able to take any decision what to do. So at least in this case, 1/3 faulty nodes are there. I think faulty is not a good word. Malicious node. Of course, you can use faulty also, but faulty is relatively much better than malicious one. So 1/3 malicious node and 2/3 regular node. So this, if this is the situation, no problem. Okay, so this can means this Byzantine fault tolerance can stand against this problem, 1/3 malicious node. But if there are more than 1/3 malicious node, then there will be a problem. All right, so 1/3 is almost 33%, and this one is almost 66%. All right, so this is a simple Byzantine problem. Like one may ask that where this can be used, like, all right, of course in blockchain, but in general, like, the airplane system, wherein there are multiple engines or multiple components in the circuit, wherein one or two components are not functioning, and it is the responsibility of other components to make sure to identify the not working components, put them aside, and take the decision as a backup system. So for such kind of mechanism, this Byzantine fault tolerance system can work. All right. Now, in case of nuclear power plant, rocket system, wherein multiple components combinedly make decision, and if one or two components are not working, got faulty, then in that case, aeroplane should not crash. All right, the regular components should be taking over, and they should take the appropriate decision so that the safe landing is done. All right, so this is distributed consensus Byzantine fault tolerance. Now let us try to compare these with our regular mechanism. So rather than generals, now we are having computers over here, because these are computers, or what you call them, nodes. All right, so these are all nodes, and physically they may be very far from each other. So let's say these are few nodes, and let's assume that these are all miners also, means they can create, they can create blocks also, and that blocks can be added. And current situation is in this particular, everyone is having the same copy of chain. So let's assume that there are 3 blocks. Of course, that cannot be 3 blocks, but for the sake of simplicity, we are assuming that there are 3 blocks in the chain, and everyone is having an updated copy, the same copy of the blockchain. All right. Now the thing is, let me put some connections also, so that we can come to know what is the connection. These and these two are talking. These and these are talking. Okay, these are means when there is a time for propagation, the block propagation, this chain or these links would be followed. Right, so let's take some random links. Okay, so this is a kind of network. All right, these are all machines, and these links are nothing but through this link, this machine can inform to this machine, something like this. All right, so now let us assume that there is a block which is added over here. Okay, let us assume that this particular machine has created this green block. Okay, and one more machine, like the question just that participant just asked, this is a purple block and this one is the green block. These two are legitimate block, but we cannot add in this way. If it is a green block, means we have to decide whether to go for green block or go for purple block. If it is green block, then this green block should be propagated across the network, means the 4th block of every copy should be a green one. Or if it is a purple block, if we decide to go for purple block, the 4th block of every copy should be a purple one. All right. So this is the problem. the question which was asked just now. This is the problem. So now if we put this problem aside for a while, okay, there are mainly two challenges over here. Of course, at the end, we would be coming to this point only. The first challenge is the challenge of attacker. Okay, so what is that problem? Attacker means, suppose you are already having a blockchain over here. Okay, then one option is somebody trying to change this block. Okay, so it would not cause much problem. Why? Because first thing is, it's difficult if it has to, if the attacker wants to change this block, it has to change this one also, it has to change this one also. All right, and if the means whole copy, whole chain has to be changed if you want to change a specific node from the middle, and this is not done. And this is only one copy. It has to be done across all the copies. So practically nobody is going to do that. So we are not talking about this part. This part we are not talking about. The main attacker part is what? The attacker trying to add. The attacker trying to add a new block, which is of course malicious. Okay, new block at the end. So where it is added at the end, nobody would be doubting, because in normal scenario the block is added at the end. So but in this case, this has not been added by the legitimate miner. This has been added by the the attacker. So in that case also, the thing is, this particular block should be validated by all other, or at least majority of nodes. And if there is a lot of checks before adding this block, it's not very simple that you can just go and simply add the block. Let me show you. There are almost 2 pages worth checks. If I'm having that stuff. So this is a GitHub link for validation. Almost this is a C++ code. All right, this is a C++ code for adding. You can see Bitcoin's src validation.cpp, and almost there are more than 4,500 lines. If I can see, yeah, almost 4,689 line for validation. This code is just for validation. Validation means before adding a block into the chain, these many validations are required. And if the block passes through all this validation, then only the block would be added. This is how secure it is. Right, so this is my challenge number 1, attacker trying to add a block at the end. All right, and second challenge is competing chain. Now this is something what is more interesting. Competing chains. Okay, so what is this? What is the problem over here? Like computing chain. Let me show you over here in a new slide. Supposing I'm already having a chain like this. Supposing I'm already having a chain like this at some node. All right, at some node A. And at B also I'm having the same kind of because right now there is no problem and every node is having their same copy of the chain. But now at A, after A, there is one legitimate, means this has not been added by a malicious miner. This is a valid miner. And as we said that there are 2 different blocks which have been created almost at the same time. The question which was just asked, almost at the same time. So this both of them have been added. But because we cannot add 2 blocks at the same time, at the same place, we can only keep one and discard the other. So what to do? Should I stop the mining process and decide whether the purple is right or blue is right, or which one to keep or which one? No, the approach is very interesting over here. Approach is let both of them be there. No problem. Let both of them be there. Now, if a third block is created and third block is added over here, for example, in next 10 minutes. Huh? This is during T1, this is during T1, okay, and this is during T2. So during T2, one more block is created and added over here. And during T3, let's say during T3, some next 10 minutes, one more block is added over here, T3. All right. So now this problem is what they call fork. Over here, the fork is created. Means there are two chains. Sometimes there'll be multiple chains. Right now, the example is two chains, but there'll be multiple chains. So you consider this as chain one. We consider this as chain two. And for both the chain, the first three blocks are okay. They have been agreed upon, the first three, but the other are not sure. So what to do? So in this case, the simplest and most interesting logic is to keep the longest chain. To keep the longest chain. Keep the longest chain. So in this case, we will be keeping this chain and we will be discarding this block. And this chain would be then later on propagated to B, and then this will be considered as a final. So this is how the problem, the second problem of competing chain, when due to a slight time lag or slight time delay, multiple nodes are added in the blockchain. In that case, let us not try to remove anything. Let those chains go as they are, and then after some time we will be keeping the longest chain and the shortest chain would be discarded. All right. So if the shortest chain, in this case, there is a one word for this. This one is called orphan block. And the miner who created this block would not get any mining reward. Right. So sometimes, you might have heard that the mining rewards do not get released immediately. The reason is this one only. Okay, even if you really mined the block legitimately, the block was valid, the block was added also, but at the end the block was discarded due to this problem. So the block becomes orphan block, and the owner, the miner of that block would not be getting the reward. And the transactions which are there in this orphan, because this orphan block did have some transaction, let's say T21, T22, T23, something like this. These are all the transactions which were there. So if these transactions, if this T21 is already over here, T22 is already here, but T23 and 24 are not there. So it has to be incorporated in the next one. So T23 and T24 has to be incorporated in the next blocks. All right. So orphan block is something which was legitimate, which was created by a valid miner, but unfortunately it was not considered in the final copy of the chain. So this is something what is the problem, what we call competing chains. So in case of Byzantine fault distributed mechanism, these two challenges one would look for. First one is attacker trying to add something which is not valid, which is not legitimate. So for that, I have shown you the code, and this block would be discarded by all other machines. All right, because it's not like you can compromise one machine and simply add that block into it. No, it has to be accepted by all other machines, or at least 51% of machines available in the blockchain network. All right. So, all right, so this is a distributed consensus Byzantine fault tolerance. And the main challenges that I've just discussed, the first and second. First one is attacker. And we are not talking about attacker attacking in the middle, but attacker adding the last one. And the second problem that we have just seen is, competing chains. When we have two or more valid blocks, but we cannot keep them all. So there is a logic of keeping a longer chain and discarding all other one. Right. So with this one, let's move forward. That in this case, what are the different types of consensus protocol? So there are two broad categories: permissioned protocol or permission model and permissionless model. So permission is basically a private one, right? So only a restricted set of users have the rights to validate the block transaction. Means you can be doing this in an organization for a specific organization. If you wish to do it, you can have permissioned blockchain or private blockchain. All right, but permissionless blockchain, or sometimes they call it a public blockchain. So public blockchain is something like our Bitcoin, wherein it does not have control of any specific organization, and anyone can come in and anyone can participate. All right. So these are two broad categories. And if we put some specific algorithms into this one, like in permission, we are having two broad categories: synchronous versus asynchronous. Because if we assume this synchronous, it's a very tight assumption, because on internet it's very difficult to assume a synchronous network, but you can have it for a very small amount of computers and operated from the same geography. Then this can be possible, but in normal case it would not be synchronous. It would be asynchronous kind of stuff, wherein the clock at Australia would be showing something different and clock at Canada would be showing something different, which is a very normal case. All right. So in both of them, we are having different algorithm. In case of permission model, we are having RAFT, Paxos, and BFT, Byzantine fault tolerance algorithm. And in case of asynchronous, we are having practical Byzantine fault tolerance. We are having delegated and federated. These three algorithms. But of course, this all under permission, means we will be, the whole network would be controlled by an organization, something like this. All right. But the second part is a permissionless model, wherein it's a public thing. Permissionless is public. Anybody can come and anybody can join the network. Okay, and the most important, or the thing that we have been discussing is proof of work (POW), which is used in case of Bitcoin. We have other like proof of stake, which is in case of Ethereum. We have proof of activity, proof of location, proof of importance, Proof-of-Elapsed-Time. There are many different algorithms under the category of public blockchain or permissionless blockchain. We would not be going into the detail of all of them. All right. But let's take small comparison between proof of work and proof of stake. I think I saw one in the schedule itself on Tuesday or on Thursday. There was a lecture from Professor Bhavesh Boisania, who the topic was this proof of work only. So I hope he must have taken these things in very much detail. But as I said, proof of work is all about Bitcoin that we are talking, and mining and all those stuff. And this one is Ethereum. Okay, so over here it is a requirement to define an expensive computer calculation, also called mining. So main problem with this one, proof of work, is mining, because what you require is a lot of time. The first thing is you require a lot of time. The second thing is you require a lot of hardware investment. All right, hardware investment. And electricity would be very huge. Okay, so these are three main disadvantages of proof of work, and to address these disadvantages, only other consensus protocols came into picture. And over here, anybody can come in, and like you have to have something, or you have to be a member of something. No, it's not like that. But in case of proof of stake, the creator of a new block chosen in a deterministic way, depending on its wealth, also defined as stake. So anybody cannot just, of course, you have to be part of the network. But suppose the total stake, total wealth is, let's say, 1000 BTC of this network. And out of 1000 BTC, Mr. A is having 10 BTC. Okay. And Mr. B is having 20 BTC. So this is their share. This is their stake. Okay. And because they are having their stake, they are having their interest in the network, they are having their property in the network, it is assumed that they would not behave maliciously, because if they behave maliciously, they are going to lose their stake also, they are going to lose their wealth also. So this is the fundamental idea behind this proof of stake. All right. And if there is a competition between A and B, then the priority would be given to the entity who is having more wealth. Okay, so it is assumed that B is having more wealth than A in the network. So B is prone to, like, less prone to be behaving in a malicious way. So this one is more trustworthy, this one is less trustworthy. So this is a kind of logic which is used in case of proof of stake. All right. The second comparison is about the mining reward. Okay, so the reward is given to the first miner who solves the problem. All right. And over here, there's no mining reward, but there is what they call it transaction fee. Okay, so the miner is not a good word, but the the entities, the computers who adds the block into that one, it is called the transaction fee. Okay, and third one is network miners compete to be first to find the solution for the mathematical problem. So there is always a competition, huge competition over here, right? Because everyone is trying to solve the puzzle. But over here, currency can be several thousand times more cost effective, because see, the problem over here is out of A, B, C, D, E. Suppose there are 5. It is having 10 BTC, it is having 20 BTC stake, it is having 30 BTC stake, it is having 15, it is having 8. Now in this case, C is having more stake. So it may happen that C may be given more chances to mine the block. And in this case, C will get more transaction fee. So richer will be more richer, something like this. So this is a disadvantage of proof of stake over here. So this is just a basic idea about the proof of work and proof of stake, which they come under the category of permissionless or public blockchain network. Okay. And if someone really wants to have research in blockchain, these are a few categories wherein you can start working upon, like, improving throughput, improving latency, the size and bandwidth, then wastage of resources. We have just talked about this part. So you can, propose some protocol wherein these resources are less wasted or not wasted, about the usability, privacy, trustworthiness of records. All right, lack of standards. I think Madam Joshi ma'am just talk about interoperability. So this comes under lack of regulation, and of course the security. So these are different, broad areas wherein one may target to, work if you are really keen to move towards a blockchain technology. Now, let me see what time do we have. Okay, we have 15 more minutes. So okay, let me ask you, did anyone tell you this one, tools.superdatascience.com/blockchain/block? If it is, I can just simply skip this. Was this tool shown by anyone? By earlier expert?
No, sir. These tools are not shown.
Okay, good. I'll take 5 minutes. This is very simple.
Yeah. So if you
And
can
in
give
fact,
a slightly introduction, then some introduction
okay.
was there. So
Okay. In fact, this is all about the conclusion of my presentation, what I have just discussed. And this particular link I have already mentioned in my earlier thing. You can see this tools.superdatascience.com/blockchain.blog. Okay. Now over here, this is a block number 1, Nonce. Now I can have some data like 0, 1, 0, 0, 1, 1, 1, 0, 0, 1. Nice. You can have any data. Okay, and just keep on observing the hash value. With every bit, the hash value is changing. And the avalanche effect. Avalanche effect means this is my message. Okay, let me add some more zeros and ones and all those stuff. Okay, now if I simply make this 0, 1, I'm just trying to make this 0, 1. Just keep your eyes on this hash value. Okay, so I'm just 1. So you can see just one bit change has changed the entire hash. So this is what they call avalanche effect. Even one single bit change from 1 gigabyte of data would entirely change the hash value. And this is why SHA-256 is being used. And then the nonce value, of course, you can select nonce value. It is up to you. So like right now it is 72,608. So I can have 502 also, right? You can have anything. Okay. But look at this. The moment I press mine, this has been changed because now I wish to have leading 40 over here. And for leading 40, the nonce value I said about the guessing part. I'll just keep on guessing, keep on guessing, keep on guessing, and keep one nonce for where the 4 leading zeros are there. This is one example. Okay, so again, you can have some changes over here. You can have some changes. And then the moment I press mine, now keep your eyes over here on the nonce because nonce will be changed. I have changed my data. So accordingly, nonce will be changed so that I'll be having leading 0. So keep your eyes on nonce. Right now, hash is this and mine. Okay, so you can have 4 leading 0 and the nonce has been changed. This is the avalanche effect as well as that leading 0 part. Now this is about single block. Now blockchain. Look at this. I am having 1, 2, 3, 4, 5 different blocks. So let me write something over here. This is my first block. Okay, so just I'm writing this is my first block. And when I press mine, look at this. The nonce has been changed and I'm having leading 40 or 50 over here. And previous hash is 0 because this is my genesis block. Okay, this is my genesis block, so I am not having leading block over here. So previous hash is 0. Suppose if I add, this is my second block as data. And if I now mine it, okay, look at this. Now previous hash is this one, 00000 CB71. Look at this CB71. And accordingly, over here, we are having leading 50. And accordingly, nonce has been changed. Now, let me put something over here. This is my third block. Then this is my fourth block. And this is my fifth block. Okay, and let me mine them all. Okay, the first and second have already been mined. Let me mine third. Let me mine fourth. And let me mine fifth. So now look at this. The previous hash is this E95C is E95C. Accordingly, some nonce values there and leading values are 0. Leading values are 0. So this is how you can demonstrate a simple working of blockchain technology to your students also. Then distributed, there is an option of distributed. Distributed means we have peer-to-peer communication. Suppose this is peer 1. Okay, peer means it's a computer. Peer 2. Peer 3. So we are having 3 different computers. Like in my case, if you remember, I had, yeah. So this one is 1 peer, 2, 3, 4, 5. And at the end, our goal is to have a same copy everywhere with every computer. So this is computer number 1. So what I'm writing is I am on year number A with block number 1. So this is my data. Let me mine this. Okay, so I have mined it. Let me write I am peer number 1, block number 2. So let me mine this and let me block number 3. Let me mine this. Okay, so now look at this. Okay, look at this. This one is previous hash is 0. This is thing. All right, 1, 2, 3. I can have some more also. Let's say block number 5 for peer A. Then block number 6 for no, this one is 5 and this one is 4. This one is 4. See, the moment I change this is also becoming invalid because this previous hash is referring to this one. So both of them are becoming invalid. Let me remind them. Okay. All right. Now, okay, this is a peer 1, means these 5 blocks are there on node number A. And now I can have something similar to peer number 2, peer number 3. Okay. Let's say A, B, C, D. I'm just writing the same stuff, and you can simply see that nonce is getting changed. Now this is taking a little longer because sometimes it's very difficult to get. All right. So same way, now the thing is, in case of distributed blockchain, now we are having multiple copies, A, B, C, D, all right? And if multiple copies are there, then only one copy would be kept and other would be discarded, depending on the logic that we have discussed. And the last concept is token. Token is like the actual transaction. For example, from Darcy to Bingley, $25 have been transferred. Now, if I simply change 25 to 24, look at this, the whole thing is changed. Okay, whole thing, and I'll have to remine everything. And when I remine everything, what will happen? The hash will change, and the next one would also change. So accordingly, 39207, look at this one. So that would change. Again, I'll have to mine over here. So I can just keep on mining. Okay, all of them. So the part which I explained that the attacker trying to change the middle one or the other block except the last one, then it would be very difficult for him because he has to change all the entire block. So this is just an example, a very simple example that you can demonstrate to your students for the sake of understanding. All right. So I hope now it's 3:25. So let's have 5 last minutes for question answer stuff.
Yes, sure, sir. Yes, participants, we invite queries, questions from your side.
I hope in my content there was not much repetition of our earlier experts.
No, sir. It was quite clear and quite distinguished content from the other lectures, sir.
Okay, so that's why I tried to be focusing more on this mining and consensus mechanism, so that at least participant would understand what exactly this stuff is.
Yes, sir. Sir, we have one question in the chat box.
What are your recent research areas? So far as, in fact, you can go through my blog at www.hbpatel.in, wherein you will find out all the details, including all those research, that is going on. But if I quickly tell you, of course, with agree on block, means I did want to show you, but I could not because, as I said, it depends on the time, but let me show you. So I think this paper is visible.
Yes, sir, it is visible.
Okay, so this is the paper which we earlier published, and it is like if someone is very novice to this domain, then I guess this paper would help understanding everything. Like this is permissionless, permission, all those stuff is there. Okay, this permission stuff has been explained in detail. All those the algorithms which I could not cover RAFT and Paxos due to time constraint. So this has been covered, including this mining and all those stuff. So this paper is, of course, with comparison all. So one may use this as a beginning. Then other is, as I said earlier in my presentation, agriculture on blockchain. So this is the paper wherein we are working on agriculture sectors, and a prototype has been defined. Okay, so you can go through this paper also if you get a time. Apart from that, there are other research like, we are working in the field of integrating IoT with blockchain to assist the medical domain. All right, that is also one there. Then self-sovereign identity is also one of the research areas for us, wherein rather than disclosing a lot of information to the verification authority, if we can disclose only one or two field and get ourselves verified, so that is also a very good research area. So there are many different research in which we are working at the same times in blockchain. The other, like I had one slides over here. Yeah, so these are all general things wherein one may plan to work upon so far as blockchain is concerned.
Okay, sir. I think we don't have more questions, and we have got so many compliments for the session. And I will also thank you, sir, for really grateful also to receive your views on the topic blockchain technology, mining and consensus protocol. And it was, as participants also shared, it was with good examples and clear illustrations. Thank you very much, sir, for sparing your valuable time with us. Thank you so much.
Thank you for having me. Thank you for having me. And thank you all the participants for listening. Thank you.
Thank you,
Yeah,
sir,
thank you, sir.
for accepting our invitation and being with us today. Your session was very informative and was very interesting, and specifically many technical aspects you have covered in very detailed manner. So, sir, thank you so much on behalf of Government Engineering College Rajkot, Department of Computer Engineering, and Team
Thank you,
FDP.
Professor. Thank you. Thank you very much.
Thank you, sir.
Okay.
So participants, we are completing this session, and we will meet at 3:45 p.m. sharp. Thank you.